Let's get started. Welcome to the webinar. I'm Sam Lindsay. I'm going to be hosting this webinar for you. You are at Next Gen Thermal Management for Defense Systems. Before we get started, there's just a few things that I'd like to go over. First, everyone here is on mute. This is being recorded, and after the webinar today, I will be sending it out to everyone who has registered. And last, we are doing some Q&A at the end. So as the presentation is going on and you think of questions, go ahead and pop them in the Q&A section at the bottom of your Zoom screen. With that, I would like to introduce our presenter today, Dr. Ryan O'Hara. He's our VP of Business Development here. Ryan brings a unique blend of technical expertise and strategic commercial leadership. A PhD-trained aeronautical engineer, his career bridges advanced materials science, cutting-edge manufacturing, and business development. With that, I'm going to go ahead and pass it over to Ryan to get this started. Oh, Ryan, you're on mute.
All right. Hey, thanks, Sam, for the introduction and prompt there. And thanks to everybody for joining. As mentioned, Ryan O'Hara, I'm the VP of Business Development here at Alloy Enterprises. And here we believe in one simple truth that defines modern defense systems, and that's thermal limits or mission limits. Whether it's radar, electronic warfare, directed energy, or high-performance computing at the edge, we're asking all of our platforms to do more sensing, more autonomy, and more computing in the same physical envelope. That means power goes up and heat goes up with it. And then thermal constraints quickly become the gating factor on delivering more capability, right? With that said, Alloy Enterprises exists to solve that problem. We're pioneering advanced manufacturing through our stack forging process, which lets us embed high-efficiency liquid cooling directly into aluminum copper components. That means lighter, more compact, and more reliable thermal infrastructure built from the start as part of the system and not just bolted on. Right? Today, I'll walk you through why this matters for defense electronics, how our process works, and what performance benefits we're delivering for our commercial and defense partners. Bottom line is this: with Alloy, thermal management stops being a constraint, instead becomes an enabler for mission success. Go to the next slide, please. So many of you in this room already know this truth because you've lived it. Thermal limits or mission limits, right? In the cockpit, operators being asked to do more autonomy, more compute, more electronic warfare in the same confined space. We've seen it. The systems fit, but the heat doesn't. In avionics bays, racks are already bursting with processors and RF hardware. Every upgrade promises new capability, but unless the cooling problem is solved, it also introduces new failure points. Thermal ceilings become the reason an upgrade stalls before it even reaches the field, right? Missiles and pods, the constraints are brutal. Diameter and length are fixed, yet we expect more sensors, more guidance, and more power. Anyone who's worked these programs knows you can squeeze in the electronics, but without innovative cooling, you can't run them at full potential. This is why we say thermal limits are mission limits. They aren't an abstract engineering challenge. They're a hard stop on mission growth that you've seen firsthand. Solve the thermal challenge and the next wave of capability unlocks. Ignore it and the mission ends at the thermal boundary. Okay, next slide, please. So this is where Alloy Enterprises comes into play. Today, we're leading the data center industry with direct liquid cooling solutions that are directly applicable to the defense market. The AI revolution has unleashed unprecedented compute demands, with GPUs running hotter and denser than ever before. Meeting these thermal loads requires advanced cooling strategies that dissipate heat at its source, capabilities we've already proven at hyperscale. Alloy now brings these same innovations to defense and industrial platforms where the challenge is identical: more performance in the same space with no margin for thermal failure. Alloy embeds greater cooling capacity within the same physical envelope, unlocking headroom for higher power systems. Additionally, we can integrate cooling directly into structural components when needed, thereby freeing up space, weight, and power for mission capability. In this image here, you can see an aluminum product on our left, and then the CT scan of the inner microchannels associated with that part. We'll get into more detail in regards to this part later. Next slide. So stack forging allows us to embed thermal management features that conventional manufacturing simply can't achieve. Right? What you see here are examples of microgeometries we can build directly into monolithic aluminum and copper blocks. We have microchannels, which give us precise targeted cooling exactly at the heat source. We have optimized fins and geometries, which increase surface area for maximum heat transfer, something you just can't get with traditional brazed plates or other manufacturing methods. We have massively parallelized flow paths, which shorten fluid travel, reducing pressure drop and pump power requirements. And because everything is made as a single piece construction, you eliminate joints, seals, and brazements, removing the failure points that often cause leaks or reliability issues with these systems. What this means for our defense customers is straightforward. We deliver cooling that is lighter, more compact, and fundamentally more reliable. Stack forging thermal management isn't bolted on, it's built in, transforming what used to be a constraint into true enabler of capability. Okay, we can go to the next slide. So here we're going to talk a little bit about performance. What we're looking at here is a direct comparison of Alloy's cold plate for the NVIDIA H100 GPU against an industry standard copper skyfin design. At a flow rate of 1 liter per minute, Alloy's plate achieves a thermal resistance of 0.015 degrees C per watt. We compare that to our competitor's 0.020 degrees C per watt, and that's a 33% improvement in thermal performance. Just as important, Alloy's design delivers a pressure drop of 0.8 psi compared to the competitor's 3.1. It's nearly 4 times lower pressure loss. In cooling, lower numbers are always better. Lower thermal resistance means the electronics stay cooler under the same load, and lower pressure drop means the system consumes less pumping power and improving overall efficiency. So why does this matter for defense? GPUs like the H100 are driving AI, autonomy, and sensor fusion workloads in the commercial sector, and those same workloads are increasingly critical for defense systems. We're going to see these same chips in the commercial sector as the defense sector, and we're already seeing it come down the pipeline. So the challenge here is that the payload volume in the aircraft pod or missile seeker head is even more constrained in the data center rack. By delivering cooling solutions that are both thermally efficient and hydraulically efficient, we're enabling higher compute densities in places where every watt and every cubic inch counts. In other words, better cooling directly unlocks new mission capability. All right, next slide, please. So, stack forging application benefits. First, we enable targeted liquid cooling with the lowest thermal resistance. It means we're removing heat exactly where it's generated, whether it's a GPU die, radar module, or laser optic. Second, because of our ability to design massively parallelized flow paths, we achieve the same better thermal performance with far lower pressure drop. That reduces pumping power and frees up system energy for the mission. Third, our components are made in single one-piece monolithic construction. Again, no brazing, no gaskets, no O-rings. We also delivered lightweighting and part consolidation. So what used to take multiple parts and assemblies is now done in one component, saving both weight and system complexity. Beyond that, we create advanced internal geometries with impingement features, gyroids, or microcapillaries that simply can't be manufactured with traditional methods. These geometries give designers new tools to push performance further. And importantly, we're delivering this today in aluminum 6061 and copper 110, giving our customers the right balance of thermal conductivity, lightweight, and corrosion resistance, depending on the application. At the end of the day, these benefits all point to the same mission outcome. Alloy is enabling our partners to mitigate heat at the source, freeing them to pack more capability in the same volume without compromise. Next slide, please. So you might be wondering how stack forging actually works. The process starts by taking a 3D model of a part and slicing it into layers along the Z direction. Each of those layers is then sent to our first machine, which we call construct. Construct takes in sheet stock, either copper 110 or aluminum 6061, and uses a laser to cut the outer perimeter of the part. We also remove material inside that perimeter to create flow channels, lightweighting, and other features. One of the real advantages here is the feedstock itself. We're using thin sheets of aluminum or copper, which are far lower cost than billet stock. So rather than machining away 90% of a billet to get to the geometry you want, we're only processing the material needed for the part. This drives major cost and material efficiency benefits. After cutting, so we print an inhibition agent onto specific surfaces, which prevents bonding in areas where parts need to be separated later. Once the sheets are cut and inhibited, they're stacked in a precise way on a caddy and loaded into our bonding machine. This step uses heat, pressure, and a controlled atmosphere to diffusion bond the sheets together. It's a true metal-metal bond at the atomic level. So there's no brazing, there's no glue, and there's no laminates. And because there's no melting, we can achieve the very fine internal features without worrying about molten metal clogging them which is a limitation of other processes. Result is a solid block of aluminum or copper with the parts embedded inside. From there, we unpack the block using strategic weak points and the inhibition layers to separate the finished parts. Finally, the parts go through a standard heat treatment, leaving us with strong monolithic components that contain whatever internal geometries we designed in, such as microchannels or advanced thermal features. Additionally, for aluminum, we can achieve a full T6 a high strength heat condition or heat treatment. And copper, we are always in an annealed state. So in short, stack forging transforms low-cost sheet metal feedstock into high-performance single-piece parts with internal features that simply can't be made any other way. Next slide. So let's shift to material properties, specifically 6061. While we also manufacture in copper, aluminum is often our most relevant choice for defense applications because of its strength-to-weight ratio. When swap is concerned, whether in UAVs, missiles, or avionics, lightweight and without sacrificing performance is a clear advantage. What you see here are tensile tests from an initial qualification program we ran for a defense customer across 396 specimens from 9 separate builds, tested in both the Z and X and Y orientations. Our material demonstrated properties that are fully within the expected range for ROT 6061 in a T6 condition. Specifically, we see yield strengths in the 260 megapascal range, ultimate tensile strength above 340 megapascals, and elongation between 15 and 20%. Important takeaway is not just the numbers, it's consistency. Multiple builds, different machines, and varied material lots all converged on stable, reliable results. On the right, you can see our tensile bars after failure. Notice the ductile necking and cup and cone fracture modes. Exactly what you'd expect from high-quality wrought aluminum, not a brittle or porous part. So in short, Alloy Stack Forge 6061 delivers lightweight, reliable, fully dense aluminum with properties defense designers already trust. And because we're using aluminum, every gram saved on thermal hardware is a gram that can go to sensors, batteries, or mission payload. Next slide, please. So we talked about tensile strength and ductility, but for many defense applications, fatigue strength is just as important. Components in aircraft, UAVs, and munitions don't fail in a single load. They're subjected to millions of cycles over their service life. This chart shows the fatigue performance of our Stackforge 6061 aluminum compared against reference data for ROT 6061. What you can see is our material follows the same SN curve behavior as conventionally processed aluminum, with no unexpected knockdowns or brittle failures. Again, in practical terms, this means that Alloy's aluminum can survive the high cycle environments defense platforms face, vibration aircraft, oscillating thermal loads in a directed energy system, or repeated pressure fluctuations in liquid cooling hardware. Next slide. So in terms of mechanical properties, we're right in line with what designers expect. Yield strength and elongation that track very closely with wrought material, which means no compromise in structural performance. Here's where we stand out. Because our process is very tightly within the 6061 alloying specification, our material carries significantly higher aluminum content compared to many wrought products. That results in a higher thermal conductivity of 187 watts per millikelvin versus 167 watts per millikelvin of wrought material. This translates into 12% more conductivity than the wrought material itself. So for defense and high performance applications, that extra conductivity is a real advantage. We also deliver very fine surface roughness, in this case 0.6 to 1.7 microns, often smoother than wrought, which means we get excellent thermal interfaces right out of the fabrication process without heavy secondary machining, akin to other manufacturing processes. It's very unusual that we have to do any other chemical processing or whatnot to smooth things out. So the takeaway here is simple. We match raw mechanical performance, but surpass in the property that matters most for cooling, and that's thermal conductivity. Go to the next slide, please. So one of the questions we get with advanced cooling hardware is reliability. Can it handle pressure? Can it remain leak tight in the most demanding environments? And the answer is yes. And this slide shows the proof. On the left is a cold plate we manufacture for semiconductor fabrication equipment. Uptime is critical and leak-free operation is mandatory. Part was externally tested for helium leak rate and demonstrated less than 10 to the minus 9 torr liters per second. It's effectively leak-free, exceeding the standards required in the semiconductor industry. On the defense side, we've pressure tested our direct liquid cooling plates to 2000 psi. It's an order of magnitude higher than typical operating pressures in most platforms, giving the system designers enormous confidence and margin in their products. Performance is enabled by our stack forging process because we fabricate a single piece monolithic structure with no brazing, seals, or O-rings. And there simply aren't the traditional failure points that we see in other processing methods. So whether in semiconductor fab that demand absolute reliability or in defense platforms under combat stress, alloy components are not just high performance, they're rugged, leak-free, and designed for mission assurance. Next slide, please. So let's talk about design guidelines. Essentially, the manufacturing limits of stack forging. Current build volume is 300 by 250 by 200 millimeters, which means we can create fairly large monolithic components. When parts exceed that size, we can also approach them modularly, but this volume covers the majority of cooling and structural use cases we're targeting today. Sheet thickness is another key parameter for aluminum 6061. We're at 352 microns and copper 110 at 413 microns. So that thickness defines the layer resolution of the process and the scale at which we can create internal features. These thicknesses have been chosen to maximize process efficiency while delivering the resolution needed to meet most thermal performance requirements. Minimum channel width is 118 microns for aluminum and as small as 50 microns for copper. Those properties come directly from the materials themselves, right? And their laser absorptivity. So both of these are extremely fine for liquid cooling and allow us to build high density microcapillary networks that you simply can't produce with conventional manufacturing methods. Right now we're producing parts in 6061 and copper 110, and those materials give us the right mix of mechanical strength, lightweighting, and high thermal connectivity. So one design rule worth noting is that each sheet layer has to remain structurally continuous for bonding, and force distribution is important. Since we're diffusion bonding sheet by sheet, vertical force transmission is required to achieve monolithic bonds. The bottom line, these are practical boundaries, but they're also enablers. Within these limits, we can create geometries that maximize thermal performance. All right, next slide, please. So now we're going to talk how we can work together, right? So when you work with alloy, you're not just buying a component, you're getting a partner across the full product life cycle. So on the left, you can see our engineering, design, and development process. We engage early. We help customers with thermal design, simulation, and qualification. It means we're not waiting for a finished CAD file to show up. We're working alongside your engineers to co-develop solutions that maximize performance within your system's constraints. On the right, you see our production capabilities. Once the design is ready, we transition seamlessly into manufacturing. Because stack forging is a digital, tool-free process, there are no long delays or expensive tooling costs. That allows us to go quickly from prototypes into production while maintaining consistency and reliability. So whether it's early stage concept evaluation or scale delivery of qualified parts, always with you from start to finish. I do want to highlight here that we can actually, sorry, Sam, if we can go back one. I just wanted to highlight that we can also turn prototypes in several weeks, right? And we can inform those decisions that also inform our simulations. Right? So we can move incredibly quickly here. With that said, I'm going to wrap up there.
All righty. So I think we are ready for some Q&A. So like I said, if you have any questions, you can go ahead and pop them in the Q&A box at the bottom of your Zoom window. But we do have some questions coming in. This is a good question. How does throughput compare to other additive manufacturing processes, such as laser powder bed fusion?
Yeah, thanks, Harrison. So just want to highlight, actually came from a strong laser powder background, right? And producing cold plates using that technology as well. So I'd say one of the two biggest things that I'm excited to be at Alloy is that there's no powder involved in our process, right? Powder comes with a lot of issues. Mostly hazmat related ones, right? And then the other piece is partially centered particles, right? And so in that respect, we don't have any of those issues. The other piece is cost, right? So you'll find that most laser powder bed systems on cost-wise are about an order of magnitude higher than what you would see with our metal sheet stock, right? In terms of throughput, we're quoting, and so we basically have 5 production systems today. And what's really nice about our production system is that, and we've done this through the material testing that we showed previously, is that since we're producing parts on a sheet by sheet layer, I don't have the issue. Maybe say there's 100 sheets in a design of a part. I can intermix those 100 sheets from different production systems and then combine them into a single diffusion bonded part, right? So if I have a yield issue with a particular sheet, I can just recut it on another machine and I can slot that right in, right? So from a laser powder bed perspective, we're incredibly fast, and then also we can mitigate some of the yield, the things that are associated with laser powder machines. Typically, you'll find, we had in previous life we had experience, a build never fails at the beginning, it always fails at the end. And that might be a week-long build, a 2-week-long build, or even a 3-week-long build. Then you have to start all over. So in terms of throughput, we're incredibly much faster. And we're able to produce thousands of parts today.
Awesome. Thanks for that. Someone has this question. Can you combine metals in one product?
Yeah, so notionally, you can diffusion bond all sorts of different products together. We're focused on copper and aluminum and single builds only. We are doing some work and would love to talk more about encapsulating materials where we actually mechanically incorporate um, uh, other materials into our process, but we are not diffusion bonding them together.
Okay. Also
Yeah.
might be worth mentioning, I think we have that spectrum at case study that people might be interested in. So whoever asked that question, it came in anonymously, go ahead and send Ryan an email. His email is down here, and we can send you that spectrum at case study where I think we did combine two different metals in that laser diode cold plate. Um, okay, let's see here. We got some other questions. Uh, Not sure how to answer this. Any potential to increase the build volume?
Yeah, so Bill, thanks for your question. Yeah, so there's nothing that's from a physics standpoint that is limiting us from growing our build volume, and that's either really the laser cutting side or the diffusion bonding side. Right now, it's purely just a capital investment piece. And then what we're finding, and maybe you have an application that's different. I'd be happy to talk to you about that. What we're finding is that we're finding this good sweet spot with the current system that we have today in the thermal regime. Would definitely like to talk more though.
Okay. This is a good question. How do you ensure bond line integrity under thermal, cycling, or vibration loads?
Okay. Thermal bond line integrity. And what was the last piece?
How do you ensure bond line integrity under thermal, cycling, or vibration loads?
Oh yeah. Okay. So I think the key there, right, is that we have specs on minimum wall thickness for our parts. We also have some IP around the diffusion bonding process that makes sure that we are able to get good bonds, right? And that's a bond line failure would be maybe a primary failure mechanism for our parts, but I have overcome that as of late and that's why we're doubling our capability. I think we saw that in the fatigue curve as well. The other key there is we can handle that a lot by design and geometry, right? So when we talk about working together, we don't expect our customers to design for our process, and that's where we like to work hand in hand. And we make sure that we have geometry that's we call it sensible. If you think about like an O in if you're going to cut out an O in a piece of material, the center of that O, we have to have that captured inside and it can't drop out, right? So we handle that on the design side, and we also handle that in some of our pre-processing software.
Okay,
Um, yeah,
cool.
hopefully that answers.
I think it does. I think that kind of leads into another sort of question. Can you comment on the technology limitations in terms of build orientation in unsupported areas?
Yeah, thanks, Sergey, for that question. So, um, let's see. Okay, so in terms of build orientation, right? So we basically either do horizontal or vertical builds, and we can align things there. And then oftentimes in unsupported areas, so we do require force transfer, right? If you're familiar with laser powder bed, they often need a teardrop shape for us, we can do circular passages up to about 5 to 7 millimeters. And then after that, we have to start going to higher aspect ratio geometries, maybe like an ellipse. So instead of a circle, we have an ellipse. And we might also have to worry about sensibility, but our designers handle a lot of that. And then the key, and I don't actually want to. So that's it might be a technology limitation, but what I'm seeing on the defense side is that we see a lot of brace parts, we see a lot of gun drill parts where the thermal passages and inlets are just really primitive, and we can deliver so much more capability in getting that initial flow in, and especially massively paralyzing it. That we don't tend to see the same limitations, and we kind of account for that.
Okay. Um, how about this? I'm not sure how the answer to this actually. Are you planning to develop high temperature options and materials such as Iconel 625 or Iconel 718?
So, Mike, I think I'm going to be a little bit facetious to say those are terrible materials for thermal management, but I totally understand that they might have unique properties for your application that you can't get around, right? Specifically, probably from like a high corrosion resistance and maybe a high temperature for something that's moving really fast. Um, Notionally, you can diffusion bond those materials. We haven't focused on that now, but I would love to talk to you more about exploring opportunities to invest in that. I will say that it would be to work on that technology would be fairly large project, but would definitely want to talk to you about that long term. We don't have anything currently in our pipeline for that.
Okay. And then let's see here. How does Alloys approach de-risk programs where thermal is a gating factor?
Yeah, so I think the key there is from a de-risking standpoint, right? So I used to be a professor at the Air Force's graduate school, and I used to challenge all my engineers about what their true job was. And it was always about design and making things better, but really at the end of the day, it was being able to identify and mitigate risk, right? And so I think that's what a good engineer should be doing. And I think in our technology enables us to put basically high performing geometry, right, in a confined space in a way that no one else can. And then so we're de-risking programs by basically removing that heat in ways that no one else can. That would be my answer, Sam.
Okay. Let's see.
Yeah.
Okay. Okay. So kind of broad, but additive manufacturing plus generative design like NTOP are a match made in heaven for increasing heat transfer density. Are there any other areas that Alloy is focusing on that drives increases in heat transfer density?
Yeah. So Harrison, thanks for your question. Yeah, you may have if you've seen where N-topology is a topology optimization software. Both Sam and I used to work at N-topology, still love the software and the things that they're doing, right? And then I kind of got I was, let's say, a combination of experience in additive, experience with advanced design tools like N-topology, all kind of led me down this thermal transfer path. I'm super excited to be here at Alloy. But the key here is that we are just there's really three ways that you can influence thermal heat transfer. I'm going to simplify the physics, right? And that physics is that you have design, right? And that design leads you to geometry that's high surface area, right? So when you think about increasing heat transfer, surface area is a big one. The other is the material, right? So in this case, we're targeting high performance geometries or materials like 6061 and copper 110. Maybe to go back to a previous question too, what's an advantage that we have over laser powder bed? We're working in ROT 6061. We're not working in a crummy cast grade material that laser powder bed uses, and then that when they powderize it makes it really expensive. We're starting and staying in 6061 right from the get-go. And then the other piece is the manufacturing method, right? You can have all the design, you can have all the great materials, but if you can't cut it and process it, then it's no good. So I feel like we have a great technology stack, and that concerns we're addressing all three of those areas.
Nice. Um, okay, I think one thing that we didn't really bring up that might be quite relevant to this audience, can you comment on ITAR compliance?
Yeah, so we are IRTech compliant and registered, and we can handle that information. And yeah, we'd be happy to partner with you on all of those things.
Awesome. Okay. Well, I think that's it. Pretty concise webinar. I'm pleased with that. As mentioned at the top, I will be sending out a recording to everyone either later today or first thing tomorrow. But thanks everyone for attending and for staying on. And thanks, Ryan, for all of your hard work on putting together this content.
Yeah. Thanks so much, guys. Take care. Cheers.
Okay.